On with chapter 13, and this is class 6, even though my heading says it's class 7. We're going to talk about helical gears. Now, helical gears are some of the most common gears that are out there. They're more common probably than spur gears. I mean, if you were just going to have a machine that was going to be kind of simple and it was going to be not used very often, or it was going to be like in a heavy duty situation and didn't need to be a high precision machine, maybe you would use spur gears. But if you were going to have something that was going to be a nice piece of equipment that was meant to last and run smoothly, you'd use helical gears. So they're pretty common compared to spur gears nowadays. And the main feature of them is that the teeth are slanted. Right, so there's like this slant to the teeth, and one thing I point out is there's right-handed and left-handed, and we'll figure out which ones how to figure that out. So one of the main things that we wanted to check out when we're looking at helical gears is to try to understand why they would be smoother than a spur gear. So here is a helical gear pair right in there. You can see these are interfacing. So I'm going to call this one the pinion, and we want to concentrate maybe on a pair of teeth. So let me see if I can point to the right one. Let's have this tooth as it's about to engage with the partner right there, and kind of take a look at that transition. As it's moving in, it kind of touches at one point first, right? And then it starts to kind of roll along. We can kind of see that it's kind of rolling along, and it kind of forms a diagonal line, right? Where there's like this, at any given point, there's like this diagonal line across, let's see if I can, across this face right here, as it starts to come down. It doesn't go straight across, it kind of comes down. And so it starts to roll downwards right in there. So there's more of this rolling action that's taking place. So it's like the smoother transition. Now, if you contrast that with our finger puppets here, when this thing engages, it kind of engages at a full line, and it touches and rolls in here. So there's going to be kind of this slapping that takes place. And that slapping can cause noise. And as there's more torque being applied, by the way, these teeth bend, and then it has a tendency to maybe even to slap even more, because the distance between teeth has changed when these have, these previous ones have allowed for some deflection and then the new ones that are about to engage, right? So it's here, let me see. These ones are like bending right here. So when these ones finally get in, they can slap against each other and cause noise and impacts. So that's why the helical gear is quieter, right? That's making this transition. It's, instead of slapping against it, it's rolling. It's making kind of rolling from the side onto it. Now there's a number of parameters that we need to be aware of when looking at this. We can have a transverse pitch right here. Whoop, I didn't mean to make a pen. I meant to go with my highlighter. Here you go. We have a transverse pitch, P, lowercase circular pitch, lowercase p, t, and then we have a normal pitch. We can find the relationship between them is going to be the normal is equal to the transverse, or right here, times the cosine of this psi, Greek letter psi, which is the, you can think of this as the helical angle, right? The helical angle. And that really kind of looks like if I were to try to draw right onto here, let's see, I'll go to my pen and put him on there. That would be like this angle, or that's the way that I think of it right here. Let's see. Yes, it's this angle right there. That's the psi right there. So I kind of think of it as that angle right there. It's the amount of lean that's taking place. And you could also see that this angle that we might want to have, right? So we have two different views that we're taking of the section BB and section AA, and so you can kind of see from this angle right there. That one right there, that's AA. That is this section right in there. So this is the transverse, right? Which is going to be the same as really it's the equivalent of the pressure angle that we would normally be used to, right? Because think of it in, let's see if we can get the pen. Usually we have a force that's coming down this way right here, and perpendicular wise right there, this is the pressure angle right there that we want. So that's really, that transverse is the regular pressure angle that we're used to. And this other one is the, this is the normal one. Or sorry, that's like taking, from taking in this right here. So you can see there's a relationship between those two. So now we have an axial pitch and a transverse pitch and a normal pitch that we could take a look at, and we could see that the relationship between the axial pitch, circular pitch, and the transverse circular pitch is this right here. And then we could also, like if we wanted to get the normal diametral pitch, are also related to each other by way of this. So like I think the pitch that we generally or the direction in terms of whether it's transverse, normal, or axial, it's really the transverse is the one that we would kind of like associate with the spur gears, and then the others are ones that we need to consider because of the being a helical gear. You could also see, well, with these angles, here is the interrelationship of them if you needed to get to find. So if you have two of them, you know the other one is basically here. Here's from another book where they're showing ways that you can consider what these look like right here, and there's an idea of there's this imaginary radius that they discuss in that book right there, but you can kind of like get an idea of the tooth form, helical pitch circle, and one tooth right here. Some other things that are kind of interesting, the helical gears can actually be put together 90 degrees from each other. I keep trying to find a pair that's going to be just right, but I think this can only be done if they are if they have a helical angle of 45 degrees, right? So I have tried this, and by the way, I think they both have to either be to right hand or to left hand. So I have a couple here, and I wanted to try this out. I don't think I want to bring these to class because I don't want them damaged. These are I potentially could use them in my gearbox downstairs. So here are two different pinions, and one of them is a no, both of them are right-handed. It's like, how do I know? Well, they're leaning to the right, right? So if you take a look at this and we consider that, I gotta be really careful with this. I don't want to damage the pen. It's leaning to the right, right? If you set it down and you look at it, you can see that the teeth are leaning to the right, right? So these are both right hand right here. So you can put these together. You can see now they're not, the shafts would not be 90 degrees from each other because these are not these don't have a helical of 45. But I think if they had a helical of 45, we'd be actually able to get these shafts to be 90 degrees from each other, which is kind of interesting. There'd be a lot of sliding taking place right there. Be very similar to the kind of like the worm gear or even a bevel gear, more like the worm gear kind of operation to the thing. But anyway, you couldn't run these gears in this configuration, I'm pretty certain, because they kind of run off of each other. Maybe you could, but I think there'd be a lot of sliding taking place. There's probably a lot of sliding taking place anytime when you have that configuration. But I think it's an interesting application right there. So right here is where you can see this is the left-hand gear and this is the right-hand gear. And you could also say here's the line of contact as I described there for a helical gear line of contact, whereas this is the line of contact for a spur gear. And because of this lean and this axial thing that's taking place right here, we have there's an axial thrust component to the forces, similar to what I described in the bevel gears. And I probably should do the helical gears, introduce those first, do go through an example and then go to the bevel gears, because the bevel gears are more specialized, whereas the helical gears are much more common. Because of that, a lot of times it's nice to have two connected to each other, or even just build them this way, where we can have like, so instead of having, we could, if we could have two pairs where one's a left-handed, one's right-handed, of course, and they're mating. And by the way, you need a left-handed and a right-handed to be able to have a standard configuration, right? They need to be able to. But now what we could do, we'd have what we call a herringbone right there. So they I guess like the herring, like a fish, right, would have like bones, like a fish looks like this right here, right? Maybe there's the fish head, and here's the bones right there, right, of the fish bones. And here's the tail fin right there. So there you go. And here's a sad fish because he just got eaten, right? But that's the herringbone pattern right there. So the force analysis that we want to care about right here, we're going to use all those angles, and we're going to have this overall transmitted force, this W right here, that we could most easily find by drawing a box, like drawing a kind of not quite a cube, it's a rectangle, but we could write that in there, and we could see where each of these angles is taking place, right? So the most important one that we care about when it comes to the forces is the transmitted one. That's the whole point of the gear, right? Is to transmit torque, and that's the one that transmits torque, right? It's perpendicular to a radius that goes to the center, and transmitting torque. So quite often that's the thing that we want to try to find, right? So and when or the thing that we find when we find the torque from the horsepower and the RPM, we find that transmitted load. Or AKA also called the tangential component, right? They're the one and the same. And then we can find the others from the angles, right? So here is a nice, also another, I liked this figure right here. It's from another book, and where they were showing them together, right? And then the thing we kind of have to recognize is there's an axial component. And because there's an axial component, that's going to cause thrust, and we need to have a bearing that will hold that thrust. So we need to have a bearing that maybe a dedicated bearing sometimes that will we call that a thrust bearing, or we have a bearing that can take both thrust and radial support. When we cover ball bearings and roller bearings, cylindrical bearings, we'll see that is a trait that we need to know about in the bearings. So anyway, this is the example 3.9 from the text. I wanted to walk through it together, where we have this electric motor that's transmitting a 1 horsepower at 1800 RPM, going clockwise direction, in the clockwise direction as viewed from the positive x-axis, right? So here is the x-axis right there. So from viewing it that way, I guess it's going this way right there, well, it's shown right there, right? And I guess we want to try to support it at A and B. That's our goal, is to do a force analysis onto this thing. It tells us that it has a pressure angle of 20 degrees and a helix angle of 30 degrees and a normal diametral pitch of 12 teeth per inch, right? So that's the one that we care about, I believe. Yeah, this should be the one we care about. The hand of the helix is shown in the figure, right? Okay, so I guess that's a right hand. It looks like a right-handed is this, the smaller gear, right? And make a three-dimensional sketch of the motor, shaft, and pinion, and show the forces acting on the pinion and the bearing reactions at A and B. The thrust should be taken up at A, right? So here is, I guess I put, this is the slides that come with the book Shigley. So as we're taking a look, and here's the 18 teeth, here's the dimensions of this. So right, some of the first things that we want to do is, well, we were told what the pressure angle was 20 degrees. We're talking the helical angle, so we can use and we could find out what the tangential. We're going to call that the tangential, right, or the transverse. I hate that we came up with all these different names. It's the I think we're going to call it the transverse because we're using the lowercase for there. So hopefully I didn't say this the wrong way. They're saying this is the transverse one right here. Interesting to me. That really seems that seems backwards to me. No, maybe. Okay, wait a minute. I will buy that. I think I spoke out of turn in the previous. I'm not going to fix it. But yeah, here would be the one that we would care about right here, right? So that's like the pressure angle. The normal one is the pressure angle. Hopefully on class I will say it correctly. So anyway, let's see. We found the transmitted by taking the transverse by taking this right here. Let's see which equation did we use as part of that. We used this equation right in here to be able to find it. So that's their go-to equation. So we're going to find it as 22.8 degrees, and then we can also find the pitch right here. So we were given that it was 12 in the normal direction. So we're going to need to have the transverse direction has this 10.39 teeth per inch. Therefore, the pitch diameter is going to be, we take the number of teeth 18 and divide it by that transverse pitch, and we have 1.732. And so the pitch line velocity uses that and with the 1800, and then we're able to find 816 feet per minute. So the transmitted load, now we're able to find from this equation of 33,000, the horsepower divided by the pitch line velocity. And now once we have that load, the all-important load right there, right, we're able to find the other loads, right? We're able to find what the radial is and what the axial is going to be. So we have all of those values right in here, and we also have the total if we wanted to. So it's almost this is a quasi three-dimension right there. It's not an isometric. But this does give us the big picture right here of what all of these loads are going to be. And this torque right here, by the way, that's internal to the motor, right? So that torque is being like electromagnetically applied to this shaft to turn the thing around. And then this line right here is just to represent, like, where the gear is right up to the point of contact that we're making for between the two gear faces right here. So with these three forces right here, we're able to take the moments about the z-axis. So we take it about A basically, and we don't do the cross product like we did in the bevel gear. They went ahead and did a cross product, and in here all we did is just take the sum of the moments. We would take the sum of the moments, and we're able to find out what FBY is going to be right here. And so we were able to walk through piece by piece and get what these reactions are going to be, and be able to figure out what the torque is going to be, although we could have just taken the RPM and divided it by, take power divided by the RPM, but we should have been able to find this all anyway, but we can confirm it at least. And actually they do it with vectors, right? Okay, so they do it with they do accomplish this with vectors, where they make this into a force vector, and then they figure out where the position vectors are in B and C. And then they also have they write out here's the thing that they're trying to find, and then they take once they do the cross products for the thing, they're able to solve the I's. Let's see, they solve the they're able to, we already knew what the torque was going to be. Okay, so that's why they're doing the torque about the I, but they're able to solve for the K with the K, and the J with the J, and then be able to find the force, and then write what the force is at A, right? So here's the reaction force at A. So that was our goal, though, and as part of this is to find out what the reactions were at A and find out what the reactions are at B, so that we can size our bearings, and which we're going to do in a class coming up very soon. So that's just another method of doing it with, so you could work off the free body diagram, or you could also use the vectors to try to get the answer. So I have another example, and I might do that one in class and leave this video for consumption. So hopefully this was of some use. It's the longest video, but maybe I'll be able to use it sometime in the future.